It's a pleasure to be here today. This is actually my first time in Shanghai, and I'm enjoying it already, and I hope to enjoy it more. Today I'd like to tell you about my views about rethinking architecture, research, and education. And I chose the title of this talk very carefully based on an algorithm that has been used for many, many years by my friend David Patterson at Berkeley. Dave's rule is very simple. You find four-letter acronyms that begin with the letter R. And this has worked for Dave very well. And when it has not worked, it's because he violated his own rule. You all know about RISC. You all know about RAID. Not too many of you probably know about SOAR. And even though it forms the foundation of the way we build large data centers today, not too many people know about the NOW project. So Dave, when he was, let's see if we can make this work. There we are. When he was president of the ACM, wrote two very influential columns, which he published. Dave had, as president of the ACM, he had the ability to publish without peer review, and he did this. And the two papers that impressed me, the two columns that impressed me were two. The first was called 7 Reasons to Shave Your Head and 3 Reasons Not to, the Bald Truth. Now, the second column was Computer Science Education in the 21st Century, which is actually the subject of this talk. But to go back to the first talk, one of the things that Dave said in his column was that if you shave your head, it makes you look younger and tougher. And I thought this would be great because I probably could use both of those things. But fundamentally, I'm an engineer and I believe in the power of simulation before taking any irrevocable steps. So I actually wound up not doing that. But the points in Dave's second ACM column were more interesting. There were only 4 of them, and the first was use tools and libraries. That is, do not try to write all the programs yourself, because a lot of people have come before you and have built valuable tools and valuable libraries, and you ought to just use those things. He was talking about things like Ruby. But in fact, the part of this discussion that struck me most was the little quote there. He said, for many CS courses, a dramatic change would simply be if students first wrote a clear specification. The final thing that he said was, build your own supercomputer. Very odd thing to say. And what he was basically doing was laying the foundation for an enterprise called RAMP, which has actually led to my latest projects and the thing that I've been doing over the last few years. RAMP stands for Research Accelerator for Multiple Processors. And the idea was spawned at a hallway meeting at the International Symposium on Computer Architecture in 2005. I didn't get didn't become aware of this project until about 9 months later, but it was a consortium, rather unusual consortium, between 6 of the top universities in the US that do architecture research. Berkeley, Stanford, CMU, MIT, University of Texas at Austin, and University of Washington. And these guys had some ideas about how to help in computer architecture today in the 21st century. And the problem for computer architecture today is that, as with real architecture, that is, architecture that creates wonderful buildings that are around us and the bridges and the roads and all that, ultimately it's about building things. And of course, the things that are built are the computer systems which we will program. And these things have to be functional, elegant, and cost-effective. Those are the 3 tenets of architecture. The problem with this is that academic departments haven't been able to actually build computers since about 1982. The reasons are very simple. in order to build a real computer system, you have to build a real integrated circuit. And the price for building a single integrated circuit has escalated exponentially over the last 20 years. It now stands for a chip that would be competitive with the microprocessors that you could buy from, say, Intel or AMD, about $40 million. This is more than even the NSF can spend. It is more than Microsoft can spend. And secondly, chip design has become too complex for small student teams. If we look back to 1982, when the RISC and the MIPS architecture were being developed at Berkeley and Stanford, that was not true. The teams were about 10 people, and they could actually build computers that work. Those days are now gone. And the result of this, in my view, is that for about the last 20 years, architecture research has become quite incremental. What happens is people studying architecture will take some small element of an existing architecture and propose changes to it and simulate those changes using a standard set of simulation tools that pervades the academic community on a standard set of benchmarks that pervades the academic community, and that's a least publishable result. And in my own view, that is fairly boring. We don't see big picture papers anymore. You can't get them published. So the RAMP idea was very simple. It was to provide a field programmable gate array based platform for architectural research. Now, field programmable gate arrays are a fairly new thing in the world, and when I describe them, I do it as follows. Think of a sandwich. There are two layers of things that are happening. On the top layer is some raw, uncommitted logic, memory, and wires. And on the bottom layer, there are a large number of static RAM cells that reach up onto the top layer and configure it and tell it what to do. There are no computers involved whatsoever in this so far. So the way one actually makes a field programmable gate array do something interesting is to write a program in a hardware description language, typically Verilog or VHDL, and compile it just as you would if you were writing a software program and compiling it to run on some architecture, except that in this case what is produced is not executable code, it's the thing that is loaded into that configuration establishing layer. When you do that, and you load that thing in and start the chip running, it takes on whatever personality you gave it in the Verilog code or VHDL code that you wrote. I was initially quite skeptical about this, and I said to Dave, I made the two objections that you see on the slides to Dave. One was that FPGAs were not big enough, and secondly, that design tools would not be up to the job. And Dave said, how long ago has it been since you looked? And I said, about 5 years. And he said, go look again. And I was wrong. I was absolutely flat out wrong, and he was right. I was right in that this project, which was to produce an engine for the RAMP program, is not a good thing to be done by graduate students, because the graduate student spends a large fraction of his or her time learning how to run arcane CAD tools, which will be fleeting at best. They will be improved, they will be changed. The student will wind up in an environment where those tools don't exist, and it's not a good use of a graduate education. So we at Microsoft offered the RAMP folks a deal. We offered to build them a platform called B3, and we spent 3 years doing it. Now, B3 has 4 of those large field programmable gate arrays, a large amount of memory, and a lot of input-output. No computers yet. So here are the subsystems, and it's a very regular architecture. The gray things are the field programmable gate arrays. The green things are DDR2 memory, a lot of it. And the blue things are the input-output. So you can both have a lot of input-output on the same board between the FPGAs, or you can go to external interfaces which allow you to plug those machines together into a larger complex. The Berkeley folks wanted to build a 1,000-core mini-core machine with this platform, and they have done so. So the project was a little unlike many of the projects that we have done at Microsoft Research in the past. We didn't actually provide funding for graduate students. What we did was we built the platform for them. We collaborated with Berkeley to write a detailed specification, engaged one of our business partners, Celestica, to do the implementation. We thought that this was much better than burning out graduate students, and we thought they could do a lot better than graduate students can do in building this platform, and we were right. The actual layout of the printed circuit board was done here in Shanghai by a Celestica engineering team. The signal integrity work to make sure that the printed circuit board would actually work when it was fabricated was done in Toronto by two groups of people that I never met whatsoever. All interactions were carried on with email. It worked flawlessly. The resulting board worked the first time. This is the first time in my career something that I have built actually worked the first time. Usually, you spend a lot of time correcting your mistakes. So we licensed the design at no charge to a third-party firm called BCube, which was set up to distribute and sell and support the systems. And they've shipped 75 systems to date all over the world. Some here to China, some to Europe, quite a few in the US. And we also supplied some of the basic intellectual property for this system, in particular a controller for the RAMs, which I guarantee is something you never want to write yourself. And what this meant actually was that both academic people and industrial people could buy them. And had this been founded by an NSF grant, that would not be the case. I went to the project originally and I said, I would like to have one of these predecessor machines, the B2. How much do I write the check for and to whom do I write it? And they said, we don't know. So in order to make it more generally available to the world, we have licensed it, as I say, to anybody for research purposes. This is good for a lot of people. If you're Berkeley or Stanford or so on, and you have a lot of money, then it's a nice platform for doing very aggressive kinds of things. But as a teaching platform for teaching students about architecture, it has the problem that it is very pricey. A B3 costs about $15,000 US, and that's too much for many people. It requires a tool infrastructure that is pretty complex, and so we wanted something simpler. And we had been looking at the project as a whole, that is the RAMP consortium, and we discovered something a little bit interesting, which is that although they purport to be about research in multi-core architectures, they didn't actually have a multi-core machine. And so I thought, well, we know how to design computers, so let's do that. And that led to a project which has occupied about the last year and a half of my time and the time of some of my colleagues at MSR Silicon Valley, called Beehive. And what Beehive is an FPGA mini-core system. It's 13 RISC cores running at 100 megahertz with 2 gigabytes of memory attached to it. It has a display controller, an Ethernet controller. It's about 6,000 lines of Verilog code. Now, this is a computer that is competitive with a PC of perhaps 8 years ago. It's not as fast, but in aggregate, it probably is as fast as that 8-year-old machine, so you can do a lot. But that's not the major point. The major point of a system like the Beehive is that a student can understand it and modify it using only the basic tool set supplied by Xilinx. We did not depend on complex CAD tools, and so we also used for it a very low-cost development board that Xilinx supplies to academics for $750. Curiously enough, because we're not academics, they charged us $2,000. It comes with a software tool chain. a C compiler based on GCC, an assembler, a linker, all you need to write and run real programs. It comes with a small but growing set of libraries for frequently needed things like printf and malloc and the other friends that we all know and love from the C systems. Like the Beehive, or like the B3, we license it for academic research use with no strings. Here's the board on which it runs. This is a Xilinx XUP V5 board. Xilinx built this board actually to run a copy of the OpenSpark system that was released into the open source community by Sun Microsystems. You can get one OpenSpark core on this board. You can get 13 Beehive cores. So this is hardly a multi-core platform if you want to use OpenSpark. So here's what the CPU looks like. You haven't seen a picture like this since an architecture book of perhaps 25 years ago. It's very, very simple. It's a 3-stage pipeline. It's 32 registers, 3-instruction pipe, simple caches, and there's only one slightly curious thing about it, which is it's a decoupled architecture. That is, memory references are decoupled from the memory system itself by those queues that you see. The address queue, the write queue, and the read queue are the way the core communicates with its external environment. And the external environment is two things. One, it's a local set of I/O devices, including a very fast multiplier based on a digital signal processor, the D-cache itself, and a couple of kind of interesting things. A messenger unit, which can be used to send short messages, that is up to 60 words long, between cores without using the memory. This is something that people haven't done for quite a long time, but we believe it holds considerable promise for simplifying the way people use such systems. And then there's a lock unit, which does the same thing for a set of 64 binary semaphores that can be shared between the cores without going through memory. Okay, so the instruction set is very simple. It's the sort of thing you learn about in Computer Architecture 101, but we wanted to make it simple enough so that students could understand it and get the basics of how computers actually work. And it has essentially no surprises except that the way the memory accesses work, which is to decouple the generation of an address from the consumption of the data, and the support for constants. One of the interesting things about this system is that it does not use a bus to connect the 13 cores to its memory. And the reason for that is if you implement a thing like this on an FPGA, you find that if you use a lot of buses, you run out of wires because there aren't enough wires on that upper layer to carry all the signals that you need. So what we did about that is we used a token ring which passes through each of the cores, the display controller, the Ethernet controller, the DRAM controller, and the model for this is a train. And the train contains a token which runs around, that's the locomotive, and it goes past a number of remote stations. And at each remote station, the locomotive declares how long its train currently is, and the remote station says how many cars it would like to hook onto the end of the train, and then the remote station counts down that number, hooks its things on, and the locomotive updates its count. And this is all very simple. It does work very well, but it does have one little problem, which in fact we missed completely. Note that in this memory controller, which is the thing down on the bottom, there's this thing called MQ. That's a large queue waiting to hold a train that is coming around the ring, but which is not terminated yet. And you must not start sending things into the ring until that until the end of the current train is reached, because otherwise you could get a collision between a new train and an older train. This was a perfect example that if I ever write a book about design, I will cite. This is an example of grabbing on to an attractive metaphor too early. And what happened? Well, as you'll hear in a moment, this system is now being used as a basis for an undergraduate lab course at MIT. And one of the MIT undergraduates one day stuck up her hand and said to the instructor, why is the engine at the front of the train? Why is it not at the back of the train? And if you do that, and you carry through the implications of that, what you discover is that you make every one of the cores, that is the remote stations on the ring, a simpler design by quite a bit. And you eliminate the need for that queue. So there's a perfect example of not grabbing on to what you think of as an attractive metaphor before you've actually thought through all the consequences. It's also an example of never underestimate the power of a smart MIT undergraduate. Okay, the architectural curiosities in this system are it does not have coherent memory. I give another talk in which I argue that coherent memory is something that we should leave behind now in the 21st century. It does not have byte addressing. Byte addressing was something that was introduced originally on the PDP-11. It's been with us ever since, and it causes a lot of problems. We have to fudge it because the compiler infrastructure that we use doesn't know how to compile for a non-byte addressed machine. So we must fake this. It has no protection. That is, a single process can smash any other process. Now, our view about that is that we have ways in software in the 21st century to get this effect without adding complex hardware and therefore adding more energy and slower performance. And so we ought to do that in software. It also has no virtual memory system. Virtual memory was a fine 20th century invention. It served us well. It's been used for a lot of good things in operating systems and as a protection mechanism, but we also have ways around that in the 21st century. So we actually argue that perhaps we ought to rethink a lot of those things. It has no kernel mode. Kernel mode is another way, it's another form of protection which you don't really probably need anymore. So the uses of the thing, well, as I mentioned, it is being used in an architectural lab course, and the nice thing about that at MIT is that the boards are sufficiently inexpensive that every student can have one, or a 15-student course can have one, and shared among teams. The Verilog is simple enough that students can make changes and try new things. This is much less and much similar to very much like another program, the Net FPGA program at Stanford, which was started a few years ago by a fellow named Nick McEwen, who produced a board and some courseware for teaching networking design. So the students got a board and a very simple Ethernet switch, and they evolved that over the course of a semester into a full blast internet router. And they were really able to learn an awful lot about how networking works by building things. The tool chain and libraries are very familiar to academics. They come in for both of the major operating systems. And the initial results of this endeavor into education on our part are pretty promising. In January of this year, we helped them teach a 2-week IAP course. Now, at MIT, they're on semester system, and the students go away for a month between semesters in the dead of winter in Massachusetts. Some of them elect to stay behind and take not-for-credit courses, which are purely volunteer. They just take them to learn things. 14 students signed up for this course. None of them dropped out. It was sufficiently successful that they decided to do the necessary work to teach a full semester course, which is called Multi-Core Systems Laboratory at MIT. And that's running now, and it looks actually fairly good. So the website for that is www.web.mit.edu.6.173. And one of the things we found as outsiders, that if you want to start a new course at MIT, the most difficult thing to do is to get the department to give you a number. Because once you have that number, you can teach anything you want. But until you have that number, you can't teach anything. So the other major use for the Beehive that we believe will be pretty interesting is research. This is a simple platform that provides a lot of the things that you need not to experiment with instruction set architectures, which are probably have been studied to death over the last 50 years, but to add various features to the architecture in order to see how they work. A couple of possibilities: use message passing instead of shared memory for inter-process communication. This was an idea that was around in the 50s and 60s, which got abandoned, pretty much in favor of shared memory. And we're not quite sure that it should have been. It has a lot of nice properties that shared memory does not have, which make it much harder for you to make the kind of errors that cause today's 21st century programs to misbehave. The one that we're interested in at this moment is transactional memory. Now, the idea of transactional memory is this is something that has been around for probably 2 decades, but has gotten a lot of interest in the last decade. There are over 500 papers in journals describing various kinds of transactional memory systems. The idea in a transactional memory system is to build a system that has many of the transactional properties that database systems have. That is, atomicity, consistency, isolation, and durability. You can't have durability because the thing that's being acted upon is main memory, and if the power goes away, you've lost it. But the other 3 you can have. And what we're interested in is not so much designing transactional mechanisms for their own, as an end in themselves, but to explore whether this is a better paradigm for programmers to write correct concurrent programs. Programmers today have a lot of difficulty with that. And in particular, the programmers that we see coming at us out of universities have a lot of trouble with it. There are a lot of problems in writing correct concurrent programs. And we have examples of how to do it written by experts, and it's still hard. And I used to think that this was a failure of the educational system, but I no longer do. The problem is that this is just an inherently difficult area of endeavor. And you can't really blame the educational system when it tries to produce students who can do it well. It's also the case that transactions, or I beg your pardon, that the kind of lock and thread-based programming that we have done to date to solve these problems does not compose. That is, if I try to build an abstraction that's a composition of 2 underlying abstractions that use locks and threads, I will have to know what the underlying implementation of those 2 lower level abstractions are in order to reason about the correctness of the composition. This violates abstraction. And if you are a computer scientist, you know that abstraction is one of the most powerful tools that we have to keep ourselves sane. And this gets rid of it. So we don't actually like that. We would like to find abstractions that do compose, possibly based on transactional memory, and experiment with them by writing large programs and seeing how they work. The other problem with transactional memory is that there aren't very many implementations. Of those 500 papers, they mostly describe software-based implementations which have extreme slowdown, factors of 2 to 5 slowdown over a lock-based program. No one is going to use such a system. So we have actually implemented in our laboratory a full blast, full hardware transactional memory system, and we're beginning to use it in order to attack this higher level problem of whether transactional memory can form a basis for better abstractions, which we think are the key to moving forward in producing better programs and simultaneously better programmers in the 21st century. So we're looking at questions like, do we really need a lot of those things that came out of the 20th century? Coherent shared memory, interrupts. All computers have interrupts. Well, not always. It turns out that interrupts were invented precisely when computers were extremely expensive. And the idea of leaving one standing idle when it didn't have anything to do was terrible because you were wasting a lot of money. Because computer time actually cost money in those days. Now, a given computer today, particularly in a multi-core system, costs a few cents. Maybe it's better to leave it idle and let it just look and wait for more work to arrive. Virtual memory, well, I mentioned that earlier, we probably don't need it. An operating system? Well, many things don't need operating systems. There are a lot of embedded systems that don't. They're good for a lot of things. You wouldn't want to try to do what you do every day with Windows without an operating system. But for many things, we believe you can get rid of it. The thing that we did not have as a goal in the design of Beehive were these. We did not want to emulate, particularly want to emulate an existing instruction set architecture. The main reason for that was not because we don't like them, but because they're not simple. I gave you the description earlier of the OpenSpark thing running on the XUPV5. Very, very complicated. And in particular, architectures that were designed for implementation in ASICs or in custom silicon do not map well into FPGAs. So the result of this is that we can't do direct comparisons with extant architectures with the Beehive system. All we can do is A/B experiments of the form, if I have this mechanism versus not having it, how much faster or different is my program? We did not have any plans to run real operating systems. We wanted primarily to run small test programs, big test programs, benchmarks, things like that. But a group at our Cambridge lab who's working with the Swiss Federal Institute of Technology in Zurich, ETH, have been building a experimental operating system called Barrelfish, which has turned out to be the exception. Barrelfish is a system that very much depends for its functioning on message passing rather than shared memory. And it also does not rely on virtual memory. So in a sense, Barrelfish was written for the Beehive, or maybe the Beehive was designed for Barrelfish. So we're looking at that as a porting target for the Beehive, and who knows, maybe we will have a real operating system running on it. We had performance as a non-goal. And the reason for this is you cannot have high performance with FPGAs anyway, because the fundamental logic is slower than it would be if you built the custom silicon chip. So all you can do in an FPGA-based system is try to do research that can inform people who design, quote, real implementations. You probably shouldn't think about building competitive applications on FPGAs yourself unless you have a very specialized thing that doesn't do well on a fundamental von Neumann architecture, like say crypto, or certain kinds of signal processing, because signal processors are very efficiently implemented on FPGAs. But we did want it to be fast enough to run real programs faster than a simulator. Much of the work in architecture over the last 25 years has involved a tremendous amount of simulation. And a number of people have built very complex systems for simulating things and for twiddling the parameters of the simulations, and doing a lot of things without ever doing any design. Unfortunately, the programs that you can run are pretty short. And if you want to run them on a multiple processor system, you can't run more than a few seconds of execution unless you're willing to spend weeks and weeks and weeks. So we wanted something that would allow you to boot real operating systems if you had them and be fast enough for that. And as I say, the machine is about as fast as a 10-year-old or 8-year-old PC. Whoops. So the next step in this project are to port it back to the B3 and use it for larger things. Use it in our own research at MSR. We're quite interested in architecture these days because we're getting to the point where we can no longer leave the hardware on which our systems depend to external people. We need to be able to talk to those people on their own ground. And so the first example for that is the Xbox, where we were intimately involved in the design of the fundamental hardware. We do it carefully. We do it probably slowly, but we're interested in it. As I mentioned transactional memory and gave a few examples. That's being done in our Silicon Valley lab by my team. The Barrelfish operating system I also mentioned is being done in Cambridge and ETH. And we want to make it more widely available for academic use. And if you want a license, you can just send me email and I'll send you back a license for research purposes. So I will run slightly under time, but I'll give you some final thoughts. My belief is that computer architecture research has been in the doldrums for 20 years. We've been waiting for the new winds to blow our ships in some direction, and it hasn't happened. Now, we actually have not so much winds, but waves. And we need to figure a way to get around those waves or beyond them. And those waves are basically the fact that we can't build faster single processors in the 21st century. We just cannot do it. Present silicon technology has not yet run out. Moore's law is still with us. But limitations on power and the communication of signals around the chip will require very fundamental changes in the way we architect future systems. And so, for the first time in a couple of decades, we have new approaches to teaching and research in architecture. And that is your job, so I hope this talk has helped you perhaps to think about that in another way. Thank you very much.
Wait a minute. Yeah, wait a minute, Chuck. We have Chuck. We have 10 minutes for a question if you are like. Yeah, if you have a question to Chuck, please raise your hand that side. Please pass the microphone to the professor. Yeah. Microphone. Yeah.
Dr. Thacker, thank you for a wonderful talk. And we have been watching your work on Beehive for some time. And I was wondering, can, for instance, a graduate student using your Beehive to build a new type of web browser within a semester?
Well, web browsers are ordinarily application programs, and so I think the answer is yes, but that's what you would ordinarily do in the programming course, not in the architecture course. Now, of course, if you had some new idea about how to use hardware to accelerate some web-based activity, then sure, I think they could. Yeah. But I think what you're talking about is primarily something that would ordinarily be done in a programming course as it is today.
No, actually what I meant was, suppose I already have a new browser ready, but I need to optimize it on a new architecture. I think today's architecture is bad. Can I use your Beehive platform to engineer a new architecture?
I think so. I mean, there's no reason that you can't pick up that core and replace it with an entirely different core. It has a very standardized interface to the rest of the system. So yes, I think you could. I mean, we have examples of that in the system itself. There are specialized processors that do things like run the display and do high-speed block copying and a few other things, calculate Ethernet checksums, mundane things, but those are examples of specialized processors for particular things. And if you had something like that you had in mind and a good idea, yes, I think a talented undergraduate could do that in a semester.
Okay, thank you very much.
Yeah. A session to the questioner. Please tell us your name and your university first before I ask a question. Thank you. Next one. That side. Okay. Yeah, please.
So as we know, as multi-core system becomes pervasive, as we know, as multi-core system become pervasive, so there seems some challenges for operating system and also the concurrency program models. So my question is, so in order to efficiently utility the multi-core systems, so is it necessary for us to develop some complete new operating system or restructure or based on the existing operating system to handle the multi-core system?
Is it necessary to have entirely new operating systems? I doubt it.
Yeah,
Operating systems have evolved in an ecosystem of hardware over about 50 years. And is it necessary to make huge changes? Probably not. But the interesting question is to look at today's operating systems and ask, what are the mechanisms that they use that the hardware is not particularly good at doing? And I'll give you an example. Hardware is not particularly good at digging out the last bit of instruction level parallelism in a program that the programmer thought about as being sequential. It spends a lot of energy to do that. And one of the new things that we have as a problem for our field is the consumption of energy, because computers are consuming a larger and larger fraction of the world's electricity. So we need to do computation more efficiently. One of the ways to do that is to rethink our underlying architectures. Does that help?
Okay, yes, thank you very much.
Yeah. Professor Yurizawa. Yeah. Okay. Another question.
Aki Yonezawa, University of Tokyo. I'm not an expert of the architecture, but so in your slide, you listed up many sort of the features of the architecture you are designing, you have been designing. And among that list, such as FPGA based or multi-core or transactional memory and message passing and so on. So which of them are sort of, how should I say, designed for the future, in the sense that you, of course, you were using FPGA. You designed the machine for convenience or more for the lightness in some sense, easy to fabricate, easy to make. But some of the features you mentioned, that the transactional memory or multi-core or message passing, are sort of looking for the future. I mean, the thing you like as an architecture. So I would like to know that which sort of the features are most promising in your perspective.
Okay, well, of course, the reason that I designed the Beehive was to be a vehicle that students could use. So that was entirely apart from the set of features that I added. I added some low-level features like the message passing system and the way the memory system worked, looking forward to ways that I thought we might use it in our own laboratory for research. I'm quite certain that anybody who is in the architecture game would pick a different set of features had they been doing the same thing. But I was doing it, and so I got to make the choice.
Okay. We have time for the last question. Yeah. Yeah, please. Last question. Okay. Thank you.
Okay, Professor, so thank you for your talk. And my question is, it seems that the B3 is not compatible for the existing ISA architectures. So I wonder, such kind of training, can such kind of training help to the students who will finally working on other ISA architectures?
Well, so far, the B3, that is the larger platform, has actually been used to implement existing architectures. One of the major projects that's been done with it at Berkeley is to build a mini-core Spark architecture machine. This is part of an effort to build a 1,000-core multi-core. So it can be used to implement extant architectures. That wasn't what we were trying to do. So we didn't want to use an extant architecture for the reasons that I mentioned. That is, that those implementations tend to be very, very complex and therefore take a lot of space within the FPGA and reduce the number of cores. We were interested in the mini aspect of mini-core research. So we concentrated on that, but we had to pick very simple cores in order to do it. Does that help?
Okay, thank you.
Yeah, thank you.
Okay.
Okay. We wrap up this session. Yeah, and another applause to Chuck for your great presentation. Thank you.
Thank you very much.